Good afternoon, everybody. This is John Barr, once again, history professor at Lone Star College-Kingwood, welcoming you to another Curious Minds episode, if you will, or webinar, whatever you want to call it. And we're very excited to have on hand today David Sumpter to speak on the topic 10 equations that rule the world. And I'm going to allow him to say a little bit more about that in just a second. Just a couple of housekeeping matters. We are mostly doing these virtual events, but we have had a couple of face-to-face events lately, and we've been able to combine those with online. So we will have one of those again on April the 22nd, where one of our history professors is going to do an examination of Homo economicus, or economic man, and the history of that project, or that view of human beings. Should be a fascinating talk, so we hope you can attend that on April the 22nd. And on April the 27th, also from Sweden, because David is in Sweden himself today, we have Johan Norberg to speak on his book, Progress, 10 Reasons to Look Forward to the Future, rather than despair about it, which is something we all probably need right now. So our series, Curious Minds, as you all know who are regulars, is premised on the idea, as the writer Gerald Graff once said, that talking about books is just as important as reading them, or even, well, that's basically the premise. And so we all invite authors to campus or invite authors virtually, and we're so pleased to have David here today. Now, David's going to speak, and he's going to give us some options about how we want to go with certain equations in the next few minutes. And then, of course, as we go through this, it's important that you ask any questions that you've got in the chat box, which is at the lower right-hand part of your screen. And we'll be, when David finishes, we will ask questions of him. And we've already got a good slate of attendees, David, and I'm going to allow you to introduce yourself. So take it away.
Well, thanks a lot. Thanks so much for inviting me. As I said, for this, there is a time difference here, and I always think it's interesting when we do it, when I do a talk like this. And so you're all having a lunch break, I take it, something like that. I just had a morning, and I'm here in the evening. So for me, I'm feeling kind of relaxed, and I've finished my day. I've actually been working from home today, but then I came into the office to give this talk, so that I'm not shouting in the office while my wife is trying to relax at home and my son is there. So it is, as John said, it's a relaxed feeling for me. So please do put in questions along the way, and I will try to answer them. But to give you a bit of an introduction to myself, so I am an applied mathematician, but I'm kind of an applied mathematician who really is on the applied side of things. So I see mathematics as a tool for understanding the world. And in that, in my job, I've used mathematics on all sorts of things. So when I first started, when I did my PhD, I was looking at honeybee societies and ant colonies and how we could understand them using mathematical models. Then I moved on to fish schools. I worked on locust swarms, homing pigeons, how they moved home together, all kind of animals that worked collectively. And you can say, well, where's the mathematics in that? Well, the mathematics is that they follow each other according to certain rules, and we can describe those rules using equations, and we can try and understand how ants choose a new nest, for example, how a swarm of locusts moves, and so on. And so, yeah, if you want to ask me questions about that later on, you can talk about it. I'm not going to talk about that today. But then I got on to another area. I started to look at human behavior and our group behavior, both online and how we group psychology and how we interact with each other, and also which can be described as mathematics. And from there, I somehow got into soccer. And what happened there really was that I wrote to some various publishers and said I wanted to write about my research. And I wrote to one of them who was particularly enthusiastic, but he said, no one's interested in animals. You have to be interested. Everyone's interested in soccer. And probably isn't that true where you are, although I think soccer is becoming more and more popular in the USA. But in the UK, soccer is the thing. And so then I wrote this. The first popular science book I wrote was Soccermatics, and that was all about how we could model different aspects of the game using mathematics. And I went on and I wrote another book, Outnumbered, which is more about social media and how we can use mathematics to model social media. But today we're going to talk about the latest book that I released. It came out in the US, I think in October. I think that this year, or I've lost track, but it came out in October. I have you're going to see the cover. I think it's quite nice here to see the difference in the covers. So in the UK version, they and this I thought was very amusing. They put my face on the front of the book, and it was kind of like the idea it was sort of my personal equations that rule the world. The US edition is a bit more neutral there. I think it's also a lovely design cover, but that's the one for the US edition of the book. Okay, so let me say, so what's the premise of the 10 equations that rule the world? Well, I need to do my share screen. So it really came to me as a kind of, after I'd written the other books, it really came to me as a kind of revelation. And the revelation came when I saw how many books there are out there which are self-help books. They're all about how you can become a better person in various different ways. Lots of them include some swear words about what you should do, but they're all about changing your life through tidying up. They're all about sort of focusing, being a better person, being stronger, often featuring scientific characters about decluttering your mind and so on. And the one I read, which is a kind of controversial book, but it made me really think about this, was Jordan Peterson's book, The 12 Rules for Life. So he had some, to me, it seemed some very arbitrary rules about how you could become a better person. And one of them was stand up straight. I have a real problem with standing up straight. My wife is always on to me. But they were things like, one of them was stand up straight. There was a few of these different other rules. And I started to think, I work with mathematics. There we have rigorous rules in the form of equations about how we understand different systems. Is it actually possible to pick out the 10 most important equations which describe life and look at them in two ways? I wanted to look at them in a very broad sense, how they're used to shape society. And also I wanted to look at them in a very narrow sense, how I can actually use them in my own life. And that's where the 10 equations that rule the world came from. And book titles, that they love this with numbers and so on. But the 10 equations that rule the world came from this idea of concisely representing the way we think of mathematics, a way we think as mathematicians in order to understand the world in these 10 equations. So what I'm going to do, as John said, I'm going to give you a series of examples. And I'm going to start with one of them, and it's this was another thing. They changed the order of the equations in the book because the American publishers were a little bit worried that you don't share the same enthusiasm for soccer as I do. And the first equation involved a betting on soccer games. They actually moved the judgment equation, which we're now going to talk about, to the first chapter, and they moved the betting equation, which is more to do with the soccer, to the second chapter. So there was a bit of adjustment on that. But anyway, so the judgment equation is the first equation in the book, and I think it illustrates some of the principles. So judgment equation looks like this. And we start, and I often like to do this. I like to start with a story which is related to our everyday experience. And I want to build and expand out from there. And so the story is this. Imagine you're an experienced traveler, having flown 100 times before, but the flight you are on now is different. As you descend, the plane starts to rattle and shake in a way you've never experienced before. The woman next to you lets out a gasp. The man sitting across the aisle grips his knees. Everyone around you is visibly scared. Could this be it? could the worst possible scenario about to unfurl? So this is a scenario, and you can think about airline travel, or you can think about something else which you find scary in your life. But this is a scenario that many of us are very familiar with. And in this particular scenario, we have a person who's familiar with flying, who's flown many times before. And what that person wants to do, that person could be you or it could be me, is work out the following: the probability that under this shaking conditions they have, are they going to crash? So they want to know the probability that we are going to crash given all the shaking. And in mathematics, we write this as follows. P is probability, crash is, well, it's a crash, shake is shaking. And so this sign here indicates given. So this says the probability of a crash given the plane is shaking. Okay, so let's take this and represent it visually. This is the 100 flights that this particular person has been on. So imagine this experienced traveler, he or she or you have been on 100 flights before, and this is the shakiest, worst flight that you've ever experienced. What we can surmise from this is if we're not going to crash, the probability that we get so much shaking is 1 in 100. You've never experienced this as bad a flight as this before. So you can actually put 1 in 100 in as your probability that you get so much shaking, given that you're not going to crash. So we've got that straight. That's your information about the world. And then you can think like this. Well, if you went on 2,000 aeroplane journeys, then you would expect to have 20 flights that were just as shaky as the worst thing you've experienced. That's a reasonable estimate of how often you'll go on that bad a flight as the one you've been on today. And then you can expand one step further out from that, or quite a large step further out of that, and you can think about 10 million aeroplane journeys. Well, why have I chosen 10 million? Well, 10 million is roughly the crash rate for aeroplane travel. So it's very rare that there is actually an accident when you travel on an airplane. So there's 10 million journeys, and inside these 10 million journeys, I've set them up here as a matrix of 1,000 by 10,000. So there's massive amount of journeys in there. There's 10 million journeys. Inside those 10 million journeys, there's quite a lot of shaky journeys, but there is actually just one journey, and this is the horrible one, of course, where there's the crash. And the probability of a crash before you get any information, before you know that the plane is shaking, is 1 in 10 million. And if there is a crash, there's quite a high probability that your plane is going to shake before the crash is. That's the nature of crashes. Though somebody told me recently that it's possible that you won't know when you really do go down. Maybe this isn't something we want to think about too much, but when you really do go down in a plane crash, you might not even feel the shaking. So it's possible that this isn't the case. But the idea here is that if there is going to be a crash, the probability of shaking is 1. Now, this is the important point. There is one crash journey and 100,000 shaky journeys. So actually, the probability that your shaky journey is the actual crash journey in all these is approximately 1 in 100,000. So even though this is the worst thing you've ever experienced, it is still highly unlikely that you're in this unlucky situation that you're actually in a crash. And I'm not going to go through all of the algebra and the maths, but this can be put into what is called the Judgement Equation. In mathematics, it's known as Bayes' rule, and it was discovered by the Reverend Thomas Bayes 250 years ago. But it allows us to collect up all the information we know, put it into an equation, and find this 1 in 100,000, exactly as I've represented in pictures just now. And what I like about this, I'm going to skip. I had a COVID example from before, but I think we've had enough of that. So I'm going to skip the COVID example now. We don't want to hear more about that. But there is ones to do with testing and so on, and if you have a positive test, and that's where Bayes' equation has come into our consciousness a lot recently. But what I want to emphasize this is the way I see it, a mathematical model, as we often call them, is like a film of the future. So a model is like a plane crash. It could be a shark attack is another example. Shark attacks are incredibly rare, but we've all seen Jaws and we worry about these things. And so, but even when you think, even if you think you see a movement in the water, it's very unlikely. If to take a positive one, the probability of getting a new job, that might be your model of the future. And the data you collect is the shaking of the plane, it's the movement in the water of what you think might be a shark, it's the interview that you have for the job and so on. And those are the data that you put into your model. What I want to emphasize now is that this is the overall representation of the equation. But what I want to say now is that some of this can be subjective as well. So when I talk about plane crash or I talk about disease testing, then that's very much an objective type of problem. But when we use Bayes' rule and we use this type of reasoning, we can also use it in a subjective way. So let me give an example of this. This example, this was quite good. I was just giving this example this afternoon. I gave a talk for the university, and some of the students were coming in and they're going to start a new university course here in Uppsala. And you can think about this, when you start a new course, you often meet new people and you're not sure about those people. Quite often you become friends very quickly, or so this is why I put in friends, because these types of people I'm thinking about now are friends you've met recently. You're not quite sure how you fit in socially with these people. And one of the worst things that can happen in such a situation is exactly this list here. So if you over here, so you've met this new group of people and you hear one of those people say something nasty about you behind your back, or maybe your friend starting at new work steals your idea and portrays it as their own, or your friend after you started this course has a party and doesn't invite you. So these are the sorts of things that they're not very nice things, but they happen to us now and again. And when these things happen to us, the question we have is your friend an idiot or not? Is this friend somebody who you can trust, or is this friend somebody you should just forget and avoid at all costs? So I've used the word idiot to describe this friend. And this is what I mean. I want to be clear here. This is what I mean by a subjective reasoning. So it's not like I go around thinking all people are idiots or anything like that. But what I want to do is make some kind of subjective reasoning about whether this friend who's just let you down is an idiot. And to do that, we need to think about our model of other people. So here is a suggested model. Again, I'm saying it's subjective here, but here's a suggested model of the world. And it is that a small number of people, 5% of them, are idiots. Now, you're allowed to choose your own level of how many people in the world you think are idiots. So I've given this talk before and somebody said, well, I think that 50% of people in the world are idiots. And I did actually think, maybe you're the idiot then, because it can't really be that bad, can it? But I don't know. Some people have this view of the world. But let's assume that 5% of people in the world are idiots. And 95% of people are not idiots. They're nice people who we can get along with well. And I've given this disclaimer. I don't really go around thinking people are idiots, or not all of the time anyway. But let's do this graphically. Here is the graphics of people being idiots or not idiots. So here's the idiots. They're in the dark area here. This has an area of 5%. Here are the not idiots. This white square here has an area of 95%. So now I've just taken these numbers and represented them graphically. Now I'm going to present some more data or ideas that I have. So what I might have observed is that idiots spend about 50% of their time doing nasty things. Now, again, this is some personal observations, but the point here is that idiots don't do nasty things all of the time. Sometimes they do nice things, just not very often. And I've divided it 50-50. So here's idiots being okay and idiots being nasty. I've divided these two into 50-50. But even non-idiots have bad days 10% of the time. And so that's represented by this number. And graphically, we can look at it here. And this is somebody who's not an idiot, who's made a mistake. We all have bad days. We all maybe forget to invite someone to a party. We sometimes say things behind people's backs that really we shouldn't have, and we didn't really mean it. We all make mistakes. And that's accounted for in this gray area here, where the non-idiots make mistakes. But what we know, because we've actually heard this person say something not very nice about us, what we know is we must be in one of these situations. It's either an idiot who's being nasty or a not idiot being making a mistake. And now comes the magic of the judgment equation, because I put these two things side by side. I've gone through the maths, I put them side by side, and I found that this area here, the dark area for the idiot being nasty, is much smaller than the area of the not idiot making mistake. And in fact, if I take the ratio of this area here and the total area, I get 20%. So there's actually only the probability that the person who did something nasty to me is an idiot is less than 1 in 5. And that's the mathematical argument about why we should be forgiving people. We should actually be nice people on the basis of mathematics. And I often feel that maths has this sort of bad reputation as being kind of hard and logical. And we were talking about this economic man and all of this reasoning about how to win over people with game theory. That's one side of mathematics, but this is actually the nice side of mathematics. It says that when we reason logically about our own subjective view of the world, we should be forgiving. And also, and I think this is also very key here, is that imagining wrong models. So what I did here is I allowed myself to think of other people as idiots, as a possible model of the world. And then I could go back from there and I could reason that this person wasn't actually an idiot. And I think that that's quite important. And it's something that we forget, is that in order to actually make logical conclusions about the world, we should allow ourselves to imagine maybe things that aren't correct, work through the mathematics or work through the thinking, and then come to the correct conclusion. Okay, so that was the first equation, and I have well, there's 9 other equations in the book. In fact, I see that one of them has gone missing. There's a universal equation as well. Yes, there we go. It popped up there as well. So what I was actually going to ask you is, first of all, if you do have any questions about what I've just said, please put them in the chat. Then secondly, maybe you would like to suggest which of the equations, of course you don't know very much about them, but which of the equations you would like to hear next, and then I can actually go on and do them. I'm not sure. I'll probably just choose at random if I don't get any suggestions, but please do put in a suggestion and I will go through one of those equations. But questions, if you have any about the judgment equation, and then if you do want a specific one of these equations, please ask.
David, one question that came up while you were talking was that if you're talking, the question is this: in talking about massive groups of people operating and mathematical models or following mathematical models, at what scale do people acting together, does the math actually, quote unquote, take over? Is it?
I mean, I think, yeah, it's a really good question. And I think I mean, it can be in small groups and it can be in large groups. So to give a very concrete example from my own research, we actually studied people who were applauding after a seminar. And there's in a group very similar to the size we have here. Maybe we have like about 20 or 30 people in a room. And what we did is we watched as one person started to applaud, how other people around them also started to applaud. And the applauding spread a bit like the spread of a disease. And that's where you have this lovely mathematical analogy between the spread of a disease and the spread of applause, which is a sort of social contagion. Mm-hmm. And what was fascinating there is that for the social contagion is that while a disease spreads, and once you've caught the disease, you just have to wait, a week until you get better. But for the contagion of clapping, there's also a sort of social recovery, we called it. So that if I stop clapping, then you'll stop clapping, and everybody stops clapping. And I think that's an interesting one because of if you do get a long, I mean, here when we're doing this, we can't do the applause thing, but if you do get a long round of applause at the end of your talk, it might not be because they liked what you said. It could just be that they're not very good at coordinating stopping applause. So the coordination problem is there. So that's a very concrete problem where even in a group of like 20 or 30 people, you actually have that kind of collective effect that you can describe with mathematics. So there's all sorts of, I think there's all sorts of levels of that. I mean, I've been writing recently for my next book. I've been writing about arguments between two people, which you can just like describe as these interactions and start to think about binary on and off switches in arguments. Oh, yeah, maybe I have to wait till I come back and I can talk in more detail about that.
Yeah, we'd love to have you back. So we've got a lot of votes on different equations, but I think the one that has won is the betting equation.
Okay, wow. I know that the gambling laws have changed a little bit in the States since I was last there. So you guys, it's interesting because that's the one that they moved from the first. That's the forbidden equation for the US edition. So
now, one of my colleagues, our librarian, says I like soccer. So if you can talk about soccer, they're happy to do that too. But anyway, the betting equation had more votes, although the learning equation had some, as did the universal equation and the confidence equation.
Yeah, well, the betting equation has a bit of football or a bit of soccer in it. So oh yeah, I forgot to show that. Let me just show you that because I forgot to show that this there is actually an equation there for each of them as well. I forgot, there's that representation and then there's that representation. But okay, well, let's take the betting equation. You can actually try this in the chat. I can't see your answers, so I don't know. So and also this maybe isn't going to work because the odds system you use in the States is very different. I actually think that the odds system that you use in the States, you have these plus 300 and minus 150. They're so confusing. Even as a mathematician, I can't work them out. I think that they're deliberately confusing in order to stop the punters winning money. But let's just try this. Is the following a good bet? You're offered odds of 3 divided by 2 for England winning against Denmark. And let's just explain what those odds mean. Odds of 3 to 2 mean that a £2 bet or a $2 bet will give a £3 profit if England win and a £2 loss if they don't win. If the probability that England win is 1 in 3, is this a good bet? You can answer in the chat if you want, and John can see your answers. Do you think that's a good bet? Have you got a? You're muted, John. So you have to.
Everybody in the audience, type in yes, no, or don't know.
Okay, they've taken one off them.
Okay, it's a mixture. Okay,
there's a mixture. They don't know.
A few more yeses than nos, and then we have one. I don't gamble.
I like the don't gamble one because that's going to be a conclusion for most of you, especially if there's a lot of yeses in the chat, because I'm afraid the answer is a no. And the way you work it out as follows is that there's a 1 in 3 chance of winning £3. That's your profitable bet. But there's a 2 in 3 chance of losing £2. So you take the win minus the loss, and you're left up with minus 1 over 3. So no, unfortunately, that's not a good bet. You lose 3.33 pence or 3.33 cents on average on such a bet. Is 1 in 2 a good bet? I don't know. You're all too scared to answer this one. If 1 in 2 is going to be a good bet,
I think it is.
I'll tell you that yes, it is a good bet. So now you're going to win 50 pence on average with such a bet because you put in the half now instead of the 1/3. Now you win 3 over 2 and you lose 1, and so you get 1. So it is a good bet on average. Now, let me just take this one step further, and I'm sorry to throw in a lot of algebra at you directly after this math problem, But what we're interested in is the following thing, and the answer's on this slide. So a fair bet is when the expected profit is 0 for both you and the bookmaker. And so if the probability that England win is P, then the expected profit is as follows. Remember, I put P 1/3 in, then I put P 1/2 in, and I got something like this. And what I can do is I can solve this, and I can find out that when P is 2/5, this is a fair bet. When you place your bet, it's equally likely the money made by you or the bookmaker will be the same. Your expected profit is going to be 0. And this is the key to gambling. So this is confusing for many people who like to place money on sporting events, is that actually everything to do with a sporting event has very little to do with if you will win money or not. What will win money for you is understanding the odds. And we end up with the following equation. I don't want to go into the details of the equation, but what I've written is Marius and Jan. Marius and Jan were 2 young students who came to me, and they wanted to set up a company winning money with gambling. And they had a mathematics background. They were very committed to this. They were very good at downloading data, and they would download data from hundreds of thousands of different soccer matches. They also bet on tennis as well, and they would download these hundreds of thousands of data points. And what they would do is that they would look at the bookmakers' odds, and they would look at the frequency of wins. Now, if the odds were fair, you expect the following relationship: P equals 1/1 plus X. And then what we did is we took the odds for recent World Cups and recent European Championships, which is another of the big international championships, and we plotted how these actual points look. So this is the data from bets on those particular matches. And what we found was that there is a small bias here, or there's 2 small biases here. What we found is that the bookmakers' odds slightly underestimate favorites with shorter odds. And this is known as the long shot bias. It says that if there's a match which is heavily imbalanced, if Brazil are playing against Costa Rica, for example, well, Costa Rica were pretty good, but Brazil are a lot better than Costa Rica. Brazil are playing against Costa Rica. You get better odds for Costa Rica to win than you get for Brazil. And that's tempting for many people. They want to back Costa Rica, but the model says you should actually back Brazil because you get a small chance of a profit, but you're much more, the odds will mean that you make that profit each time. Then there was another bias here, is when you have very evenly matched teams, then they overestimate the favorites with longer odds. So when the teams are very evenly matched, you should actually back the non-favorite in that particular match. And this comes out when we compare the theoretical line, which was this, with the data. And what the betting equation does is it adds a kind of small change to this. And this is a parameter here that we introduce, and they stretch the theoretical curve to be closer to the data. And that's what we do here. So you see that this new curve that I've fitted through the data, a new line that I've drawn, it follows this equation, and it's closer to all of those points. And this equation better predicts the matches than the bookmaker's odds. Now, there's a good chance that you haven't followed everything to do with my explanation there, but the main thing I want to emphasize here is at no point did we try to understand anything about a game of soccer. We didn't look at anything about Brazil, how they've been playing. We didn't look how the USA have been playing. We didn't look at any information about the actual games. What we did instead is we identified these biases in the odds, and then we sort of found a new model which described those biases in the odds. And that model gave us a small edge. We used that World Cup model, and we made £200 from £1,400 of bets. There's definitely some luck involved in that because there's not a lot of matches in the World Cup, but we put in our money and we managed to make a bit of money on that. But that was just a start for Marius and Jan, my students. Well, I don't want to say that they weren't my students. They were students, and they approached me. I don't send away my own students on doing these things. But they were young students who wanted to get into this and wanted some advice. But they went away and they did lots of reading. They worked incredibly hard. And I like to use this is pre-pandemic. These guys, they traveled all around the world. They learned how to do betting. They got to travel to very splendid locations. And in the end, they made a fair bit of money. In 2019, Jan Marius's model made 838,000 euros from over 100,000 €100 bets. Now, the key here is that that's less than 1% profit per bet. This means there's no luck involved in this model anymore, that they've actually shown that it works over a long period of time. So they have made a profit. But what I always want to add, oh yes, I've said that about the football. What I always want to add about this and these guys is that these guys worked incredibly hard. They used their mathematical skills that they'd learned at university to set up a company. They collected in a lot of data, had incredible computing knowledge, and they put all of that together in order to carry off this. So I certainly didn't have the time to be involved with them. Maybe I should have, I could have retired by now. But they also another key thing here is that they happened to have a friend who'd won a lot of money playing poker who was willing to invest in them. So they had to have some investment capital to do that. I didn't have the investment capital to do that either. So but they could do it. And it did involve a lot of hard work, but they made a lot of money. And now I want to get to what I think is a really important key that I bring out in the 10 Equations book. And it's this, that these, and the story for this part, it actually starts at the racetrack in Hong Kong. So this is, now I've forgotten it's a Happy Valley racetrack in Hong Kong. Very famous, well-known racetrack where all the high rollers go to gamble. And this part of the story starts there because it starts with a guy called William Bednar. And what he did is, and it's documented, you can actually have a look. There's a nice article on Bloomsbury about Bill Benter. And what he did the impossible according to the algorithm. He wrote, according to the article, he wrote an algorithm that couldn't lose at the track. That's not quite true. There's no algorithm which doesn't lose at the track. That's the whole point. If you have to make 100,000 €1 bets and you only have a 1% return, then actually 49% of your bets are losing bets. So it's not true that he wrote an algorithm that couldn't lose at the track. He wrote an algorithm which lost only 49% of the time at the track. But he was able to use that to make $1 billion. And he told his story to this journalist. But what fascinated me here is that he told his story in 2018 or something like that. But in, I think, 1996, he published a scientific article outlining exactly what he did. And the article is called Computer-Based Horse Race Handicapping and Wagering Systems, a report. It's written in a very, very dry style, it goes through every step, and it includes the equation I've just shown you, the betting equation. It says how to use the betting equation. It gives some preliminary results where he's made profits over 5 years. He even gave a talk on YouTube in 2004, I think, which is now on YouTube. He gave a talk explaining how all of this worked. And in that is precisely the equation that I've talked about. And this is what is amazing, that this is available free online for anyone to download and use. And we in science, we're very interested in how many times our articles are cited and used by other researchers. I have an article about how ants choose a new nest, which is cited 400 times. So you can just see, like, there's a very niche area, 400 times the citations. Citations of this, 100 citations. this billion-dollar equation has 100 citations. So people just ignore this stuff. You know, it's sitting there ready to learn and to use. But because people aren't using the language of mathematics, they don't always have access to these things. And I think, you know, what I do in the book is I bring out that there is, to some degree, a conspiracy theory about mathematics. I mean, we live in a world where we talk a lot about conspiracy theories, but this conspiracy theory is something that even us mathematicians aren't properly aware of. I wasn't aware of it before I started thinking about this in equations, but there is this secret code that we write to each other, that we can understand and communicate with each other, which allow us to build up lots and lots of different applications. And I'm maybe going to come on to some of these other applications, but the betting application is one. If you look at Google and how they built their search algorithm, it's based on one simple equation. If you look at YouTube and how they get people watching videos over and over again, that's also based on an equation. And it's not like a conspiracy theory like the ones that you read online, but it's a conspiracy theory in the sense that you have these more and more powerful individuals who are using these small numbers of equations to rule the world. And I call it that 10 is this secret society that we don't even know about, is basically hidden in plain sight. To the mathematician, they see those equations, they start to think how they can use them in different applications, but it's all hidden from anybody who's not very into the equations themselves. And I think that's what I'll say about the betting equation. I think we probably have time for one more equation, John, or definitely you can ask me if there's questions about any of that, any of the things I've just said just now.
Why don't we do the confidence equation?
Yeah, I think sorry, I'm just I think I don't have, do I have some slides for the confidence equation? But I think
well, we can do another one.
But no, but was there a vote for the confidence equation,
There
or
were a couple, but there were also votes for.
I'm going to tell you. I think can I just freestyle the confidence equation? If I just tell you a little bit about it, and I can actually use some of the.
Someone else wanted to look at the universal equation.
I'll come back to the universal. What I'll do is I'll talk for like 2 or 3 minutes about the confidence equation. Then I'll come back and I'll finish off on the universal equation because it's a nice place to finish. And I think the confidence equation starts also with gambling, and it starts with this idea of how long do you have to look until you know you're onto a winner. And when you've only got those 1% edges that I talked about, when you're losing 49% of the time or you're winning 51% of the time, you actually need to make thousands and thousands of bets before you know that you've got the right thing. But if I take another more everyday example, let's take reviews on TripAdvisor. So when you see the reviews on TripAdvisors and they have these different stars and so on, and you always go and you see like there's maybe one very bad review about the hotel, and you start to get really worried, and then you keep going down and you look at the different star ratings. One trick you can do is you need to think about the standard deviation in the ratings. And it turns out that normally the standard deviation is about 1 star in the ratings. And so what do I mean by standard deviation? Well, the average rating might be 3.5. But the average distance from 3.5 to the different ratings is 1. And so typically the ratings are between 4.5 and 2.5. Those would be the types of ratings. And so you want to know, if you've looked at a particular hotel, how far are you away from that? And because the standard deviation is 1, I show in the book, you actually need around 16 ratings in order to know, to be confident about the hotel. So what you should do is look at because the latest ratings are always the best ones. So you should look at the latest 16 ratings in order to get the best idea of this. And the confidence equation I love because there's so many ways in which we use it. I mean, we use it in statistics to be certain about things. We use it in sport betting to know that we're going to be winning. Another example I give in the book is if you're deciding if you're going to quit your job, what you can do is every day give a star rating to the day that you've had. And you don't want to, so you don't want to just quit it if you've had really one bad day. Give the star rating, calculate the standard deviation and the average. And then after you've maybe done this for about a month, then you have a really certain picture of how good your job is and whether you should quit. I gave a talk actually about, or I talked about this on a science podcast. And I was saying that you can also use this on your relationships. If you're in, I'm a happily married man now, so I don't have to worry about these things. But if you're in the early stages of a relationship and you're trying to work out, is this really for me? Then a star rating every day. And I thought that this was quite controversial, and maybe I don't know if people would like to be rated by other people in this way. But the host she said, well, yeah, I did that with my boyfriend and then he was gone. So it kind of backed up the theories that it can work. So the confidence equation is all about that. Is all about looking at the standard deviation and the difference to the from the standard deviation. But if I take and wrap up on the universal equation, because I think it's quite nice it's a more mathematical one, but it's kind of philosophical thing. And it comes back also to what I said about a little bit about what I said about the conspiracy theory, because I love this idea of mathematics controlling the world. And many of you, I think, will have read Dan Brown's book, or you'll have seen the film The Da Vinci Code. And it is a beautiful idea in that book that there is this number phi, the golden ratio, and it can be found in drawings of Da Vinci and so on, and it is somehow underlies the whole world. There's a whole kind of conspiracy theory built up around this number phi, and the number phi is 1.618, and it's the golden ratio. It's the ratio between if you take a rectangle and you have sides a plus b here divided by a, well, that's equal to the ratio of a and b is equal to phi. And so this ratio, the golden ratio, is kind of like a secret mathematical code. And it also underlies the end of the Fibonacci sequence. So a Fibonacci sequence is, so 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, and so on. And if you look at the ratio of the two numbers at the end, so 21 divided by 13, 34 divided by 21, and so on, they tend towards 1.618 as you go. So there's all these kind of patterns that come up in mathematics, and that's what Dan Brown really uses in his book to build up about why mathematics underlies the world. And that's illustrating exactly what I said. 21 divided by 13, 1.615, 34 divided by, and this goes over time towards the golden ratio. And there's this theory that was put forward really by Henry Poincaré, and he says the sheer number of mathematical theorems that have proved to be true led French mathematician Henri Poincaré to reflect in his book The Science and Hypothesis that if all the assertions which mathematics puts forward can be derived from one another by formal logic, mathematics cannot amount to anything more than an immense tautology, just proving true things are true. Logical inference can teach us nothing essentially new, but can we really allow that theorems which fill so many books serve no other purpose than to say in a roundabout fashion that A equals A? And in a way, Poincaré, he was being, he didn't really, this was a rhetorical question by him. But it turns out really when we look at mathematics that that's exactly what's going on. what's going on within the golden ratio is that it's solutions to various problems. All we're ever doing is saying that A is equal to A. So I write in the book that phi is a positive root of the quadratic equation x squared minus x minus 1. And solving the Fibonacci sequence and finding the golden ratio both involve solving this same quadratic equation and thus give rise to the same answer. So there's no mysterious magic code hidden within phi or any other number. It really is just the case that A is equal to A. And I think to wrap up really is to say that, well, could mathematics hold the answer we're all looking for? Well, it won't be in that type of form where we just look at the kind of magical equations of mathematics, which are hard for us to solve, but really just contain tautologies. But it could be in the form that I've been thinking about with the 10 equations, that yes, there is that way of thinking, but only when we let the data into our lives, only when we think about gambling odds, when we think about how confident we are about hotel reviews, when we think about our social connections, when we think about the data that we get from people around us, only when we allow data in and combine it with mathematics can we see that mathematics has the answer we're looking for. And I wrote this as my nice equation at the end of it. We have the data, we have the model, and we have the 10 equations that rule the world.
That's a great ending. And the first question, David, is right along these lines. And she asked it a few moments ago. It's from Kirsten. And she said, is there any type of moral or emotional aspect to the conclusions that are drawn? Or do you think the mathematical logic doesn't allow for that? So yeah, that's a great question. You're muted.
You muted me. All right, I got muted there. Sorry. It's a fantastic question. And that is the question I was wrestling with all the time when I was writing my book, because there's this idea that mathematics should be taken away from the emotion, that we should separate mathematical thinking, which is all logical and hard. And there's so many people that you hear with this kind of this kind of view that we should sort of separate away and be logical and make these steps, but it's simply not possible, because whenever we want to actually solve a real problem, we have to put the data in, and that data is often subjective. It's based on our experiences in life. So mathematics is a way of reasoning about these often subjective things that occur and happen to us, and we should never just close it off away from all of that and say that we've got the answer. And a lot of the mistakes that I think that I've seen recently in some of the discussions, particularly when our intellectuals are taken from people who are working with tech companies, who then just say, look, here is the mathematics and here is our world. We've solved this, we've built this artificial intelligence. We've built this kind of very advanced device. Therefore, closing things off gives us the answer. And that just leads us to all sorts of fallacies, because it closes the world off from all of the data and subjectivity that's coming in. And I think that we should be welcoming that instead, that we should try to find a world where, yes, mathematics is important, that we need to learn mathematics and use it in our reasoning, but no, we shouldn't allow ourselves to cut it off from subjectivity and our emotions even.
Okay, the next question is, why don't we teach mathematics this way?
Well, I struggle. Yeah, it's difficult, right? The reason I struggle with this question is my wife is a maths educator, so she knows a lot more about like how we teach mathematics or why we teach mathematics in the way that we do. And she's always resistant because she thinks, that I'm cheating a little bit now, when I do this and I tell you about the fun parts of mathematics. But you still have to be able to do the steps, right? You still have to be able to do the manipulations. Yeah. I got a little bit into that with the betting equation, that you have to know how to move things from the left-hand side to the right-hand side. And you have to be able to, you have to learn your multiplication table. There's things you have to do which you can't get away from before you get to these types of fun things. And so I think that that's one part of the answer to the question. The other part is I think that we can do a lot better. I think that we should do a lot better in mathematics. I try to bring this more into my teaching. I try to take out some of the very dry proofs and say, here are the examples that illustrate why this mathematical idea is important. And hopefully we're getting better at this. There's some brilliant videos on YouTube. I think it's 2 Brown 3 Blue, I think is called, does this amazing videos illustrating these types of things. So there's more and more stuff out there. And us educators, tomorrow I've got to go and teach Laplace transforms to the students. So this is my evening off, right? So this is where I get to say the fun things. Tomorrow I'll be sitting there drawing out integrals and the students will be asleep. So right. Yeah, there's all sides to that question.
So could you, I teach a history of spaceflight course, and we've talked a little bit about the moon conspiracy landings. So could you use Bayes' theorem to show why the moon conspiracy landings are just wildly improbable, or their views?
You can actually. I mean, you can use this. It's nice. There is a paper on that subject, and there's a very nice idea, a simple idea that if you're going to have a conspiracy, you've got to have a small number of people in it. So the rate at which the conspiracy will leak out is proportional to the number of people involved.
What's the name of the paper?
I don't know. I'll have to look it up for you later, because this is just something I read myself and it really appealed to me.
Me too.
Because it really just says, so the probability is true is just 1 over the number of people that would have to be involved with it, because basically one person's going to crack, right? And the moon conspiracy, I read recently also that there's 400,000 people helped NASA get the right. So there you've got, even there it's some constant times 1 over 400,000 is the probability that the moon is a conspiracy. So a conspiracy has to involve a small number of people, or in my case, my conspiracy, the 10 conspiracy, just involves a load of mathematicians who haven't really realized that they're part of a conspiracy theory. So I think it's a nice result. 1 over the number of people is the answer.
It's interesting you say that, because my father-in-law worked in mission control on all the Apollo missions, and that was the first thing he said to me when I asked him about it was, do they know how many people worked on those on that? So okay, so here's the last question, and it doesn't surprise me at all, where a student wants to know a little bit more about soccermatics.
Oh, that's very nice. That's very nice that you ask. I mean, I think what I would recommend is I have a very active Twitter account called exactly Soccermatics. And there I put a lot of information about how we use mathematics. But what I will say, which your students might find exciting, is that after I started working on this book, I've now worked with Barcelona Football Club, and I've been down there, and I've been close to, I haven't actually met Messi, but I've been down on the pitch observing him, and I've been to the academy that they have, La Masia. I work with England Football Club as well, looking at, they have a mathematicians who work on their penalties. They lost the Euro penalty championship, but in the World Cup, they made a big improvement on their penalty scoring. And so there's all sorts of exciting things that I managed to get involved with after mathematics, so after Soccermatics. So follow the Twitter account and you'll find out all about it.
We, in our basketball team here in Houston, the Houston Rockets, the general manager, Daryl Morey.
Oh, yes. I know him personally.
You know Daryl, right? So we pay a lot of attention to analytics down here. He was really a pioneer with that, and
yes,
made some draft choices and some trades that initially people wondered why was he doing that, and it turned out they were fantastic decisions.
He's a great guy. He wants to destroy soccer, and
right.
So I talked to him a few months ago, and he has this idea, because soccer, we love this like passing game, with Barcelona. He has this idea that they should just change everything. They should just kick the ball high up in the air all of the time. They should just have a team of players who kick the ball in the air and see if you can win the game that. So he wants to do the same things to soccer as he did to basketball.
He's changed it. Well, look, David, there's a lot of people typing into the chat. Thank you. Another one, great presentation. Another one, great webinar. We're very grateful to you for your time. We're very grateful to the audience for taking your afternoon to listen to this. And I have another comment. I enjoyed it tremendously.
Oh, well, thank you.
Very interesting. This has been a lot of fun, and I'm going to stop recording. And thank you, everyone, for being here.
Oh, thank you very much. I really enjoyed it.
Be sure to follow us on social media at Facebook, Twitter, and Instagram. Like this video, leave a comment, and hit that subscribe button to be notified about our latest content.